Astronomers believe that most galaxies have a supermassive black hole at their centre. And these supermassive black holes range in mass from 1 million to tens of billion times more massive than our Sun. And black holes are objects with such high gravitational fields that even light cannot escape from them. Radio radiation from around the black hole at the centre of our galaxy, which is known as Sagittarius A star, was first inadvertently detected by Carl Jansky, who was working for Bell Telephone Laboratories on radiostatic. These observations were confirmed by Grotto Rieber, who detected the radiation using a radio telescope that he built in his back garden. He was the only radio astronomer in the world for 10 years. But the Milky Way does not have an active galactic nucleus. I asked PhD student Kate Dutson to tell me more about them.
Yeah, active galactic nuclei. These are the systems at the cores of active galaxies. So AGN are very bright all across the electromagnetic spectrum, but they're quite rare. I mean, most galaxies aren't active. But, yeah.
The basic configuration of an active galactic nucleus is thought to consist of a supermassive black hole surrounded by a disk of infalling matter with jets emerging from the black hole. Matter from the accretion disk falls towards the black hole, and this process releases energy. And the accretion also powers the formation of jets from the supermassive black hole, although it's unclear exactly how this process happens. It's thought that in galaxies like our own, which don't have an active galactic nucleus, the central supermassive black hole is starved of infalling matter, so there's nothing to power the formation of jets or the extreme radiation.
At the centre of our galaxy, we've got the supermassive black hole, but it's dormant, so there's no AGN there. But it might have been active in the past. So.
There are lots of different types of AGN. Blazars, BL-lax, radio galaxies, Seyfert galaxies type 1 and type 2, quasars, which all look very different to us on Earth.
Basically, there's lots of different types of AGN, it's a complete zoo. So the unified model tries to put them all together and make sense of them. And the most simplistic way of thinking about it is it suggests that all AGN are intrinsically identical, but the viewing angle on which we view the system affects the observational properties. So for example, if we look straight down a radio jet, then we might see what's called a blazar, which is a type of AGN. Yeah, so the suggestion is that they're all the same, it's just how you look at them and kind of what angle. But it's quite a simplified model, so other things will affect what's going on there. For example, the efficiency of the accretion. So it's not definitely just geometry which defines it, but the unified model is mostly talking about the geometry of the system.
I asked Kate why we expect to see gamma rays from AGN.
So gamma rays are produced when particles are accelerated to really high energies, so cosmic ray acceleration, for example. So we expect AGN to be sources of gamma rays because you've got lots of different sites where particle acceleration could be going on. For example, jets, quite close to the launching of the jets. We don't actually see gamma rays from AGN other than blazar type AGN at the minute, so ones where you're looking down a jet or at least quite close to that angle.
Yeah. CTA might be able to help us see more types of AGN so that we can better understand the particle acceleration in these objects.